we learned about the Stoilov decomposition. Let's briefly recap. So given a Q quasi-regular mapping F, we find a Q quasi-conformal, so quasi-regular but actually invertible. Mapping, let's say G, and a holomorphism, a holomorphic function from G of omega into F of omega, such that F of Z is equal to phi of G of Z. Right? That is a statement of the result. And as we know, all the good stuff, actually all the good stuff about quasi-regular mappings follows from this. So this is the picture. And it's G, and this is our holomorphic function, right? So this is the classical result, but it can be extended quite strongly. And this is a theorem from the 90s, early 90s by Iwaniec and Sverak. And this is one of the papers that is on our list of things to read. So this is our result. So that K of X, let's do this a different way. So given F from omega into R2, let K of X be this quotient here of the norm of the derivative, the operator norm of the derivative squared over the determinant. Like this. And I'm going to add that with determinant of F bigger than 0 almost everywhere. Okay, so determinant of the gradient of F. So if this thing is positive almost everywhere, then this quantity is making sense, and we're also going to assume that F belongs to W12 of omega. So we can actually have weak derivatives to make this expression be meaningful. Okay, so we're defining this thing, and in the case when it's quasi-regular, then this thing is just uniformly bounded. It's just less than Q, right, if it's Q quasi-regular. But now we define this as a quantity which depends on X, and our condition, so say let K be defined this way, and assume that the integral, or an omega, of K of X dx is less than infinity. Okay? These are called mappings of integrable dilation. This is called the dilation when we have something which is Q quasi-regular, then the dilation is L infinity bounded. Now it's just an integral bound, so i.e. mapping of integrable dilation. Then there exists homeomorphism, or G, belong to W12, homeomorphism, so if omega into R2, homeomorphism, such that the same decomposition holds phi from G of omega into F of omega holomorphic such that we have that F of x is equal to phi of G of x, like this. Okay, so what have we lost? So previously G was a quasi-conformal mapping, right? It had the same control on the L infinity control on the dilation, which is kind of clear just from this diagram, right? Because we have that phi is a holomorphism. It's a phi is a holomorphic map, so its gradient is just a conformal mapping. So the way in which F stretches and distorts the unit ball is entirely encoded inside G. In fact, that's how it works. That's the way we found G, as we learned yesterday or last time, was by solving the same Beltrami equation that F automatically satisfies, right? So it's kind of immediate that G is also going to be a quasi-conformal mapping. It encodes all the way in which the unit ball is distorted, right? In this case, we are having integrable dilatation, so we can't obviously insist that G is Q quasi-regular. That G is Q quasi-conformal, because this thing is not quasi-conformal. Its dilatation changes from point to point, right? It can really distort balls into very thin ellipses at some points, so long as overall the amount of distortion is integrable. Yeah? So it's not hard to see this thing will satisfy the same. From this decomposition, we know that the F of x equals d phi of G of x, the G of x, like this, right? So the distortion of F at x is it is actually the case, is going to be the same as the distortion of G at G of x, like this. Yeah. So this thing actually will have the same integral dilatation as F does. Okay. But it won't have more. We can't insist that it's Q quasi-conformal, right? It is. So the hypothesis or the conclusion is just that it's in W12 and it's a homeomorphism. It's invertible mapping. Okay, but that is good enough, because what good stuff did we get from this? We got that F is open and discrete. Well, we still have that it's open because G is a homeomorphism, right? So by exactly the same arguments before, the image of an open map is going to be an open map because G, so let me just write it down. So if U contained within omega is open, then G of U is open because it's a homeomorphism. And so F of U, which is phi of G of U, is open. So it's definitely an open map, right? And it's also discrete, because if we take any point here and then pull it back with phi, then we have at most countable pre-images, and any cluster points are on the edge of G of omega, right? And then when we pull it back with this homeomorphism G, we have the same thing. Any cluster point has to occur at the endpoint, at the boundary of our region. Yeah, so it's also discrete. i.e. f to the minus 1 of zeta is at most countable, with cluster points at the end. because the point's not in omega. Okay, so all the good properties are still here from this, but we have a much weaker hypothesis. Okay? This is massively weaker. That's a good question. No, it's not only true in 2 dimensions. It's true in higher dimensions in the sense, in the sense that you have that you'll have a mapping that is open and discrete, and that's a paper by Manfredi and Villamor, and that's also a very nice paper. And but it's not true with quite the same strength. So you need. This is L1 integrability of the dilatation. The conjecture inside the paper of Sverak and Iwaniec was that if you had n-1 integrable, and Villamor and Manfredi, or Manfredi and Villamor, proved it when p is strictly bigger than n-1. And it was an open problem for n-1 for a long time, and it's recently shown to be not true when you have exactly n-1 by Henschel and Kai Rajala. I can't say his name, is a Finnish guy. So this is, this was a very natural thing to want to understand in higher dimensions, and it was something a lot of smart guys worked on, but now it's completely understood. So yeah, the limit of this in higher dimensions is that you need this to be a bit more integrable. You need it to be integrable for p strictly bigger than n-1. Okay, so this is the final theorem that of the 3 papers I want you to collectively or individually read, and it uses this theorem I stated about this theorem here, the quasi, the standard one, and kind of pushes it in a certain way to be able to get to this weaker hypothesis, and it's quite a short, neat, clever proof as all the papers I suggested. Cool. All right. Good. So that is that part. Now we're going to raise the board, and we're going to start to build up the background necessary to prove this theorem here, and prove this following identity. So let's call it a theorem. So that F belong to W1, 2 of omega into R2. Omega is a nice domain. It is nice, i.e. the boundary of omega is nice. And we have the following identity that if we integrate around omega, okay. So actually, we're going to do this identification between complex valued mappings and R2 a lot, but we need to state this for complex valued mappings. Omega is nice, and we're going to do this. We're going to take df by dz bar. Let's write that better, like this. And then we integrate. Okay, let me explain what that means. So I'm going to write a double integral. I'm going to write dz. I'll explain in a second. And that's equal to the integral around the boundary, or minus I over 2, the integral around the boundary of f of omega f dz. All right, so when I'm doing this, what I mean is the following. I mean Lebesgue measure in R2. So we're going to do the double integral of omega of df by dz bar, and it's a function of x plus iy, and we're going to integrate it with respect to dx and dy, just like its Lebesgue measure. Okay. Yeah. So we're integrating the complex plane, but we're just integrating it like Lebesgue measure. Right? And then this thing is our standard integral around a closed curve. So we're going to take a parameterization, and we're going to put in f of the parameterization times, what are the parameterizations called? Z. So f of z of t times z prime of t integrated with respect to t. So this is the completely standard integral, line integral in complex analysis. Yeah? Goes over 2 let me actually write that down. So integral from, say, 0 to a of f of z of t, z prime of t dt, where z from 0 to a into the boundary of omega is a parameterization, is an anti-clockwise parameterization. So every parameterization around a closed curve is for us always going to be anti-clockwise. And what this comes down to is the divergence theorem, when we work it out carefully enough. So let's get to work on this. So d by dz bar is equal to 1 over 2 d by dx plus d by dy. Right? That is our verting derivative, and we're going to write f of x plus iy as u of x comma y plus iv of x comma y in the standard way. So when we write down this thing, df by dz bar. So now I'm going to go back to writing this dz, but again, this is what I mean. If you forget this or get confused, just stop and ask me to explain again. So we write this thing. Let us do this. So 1 over 2, and let's put the derivatives through. So we have u of x plus iv of x, and this is already wrong. This is I, like this, plus I of u of y plus iv of y, like this, okay? dz, yeah? Cool, and then let us clean that up. So we have this thing, and let's put all the reals together and all the imaginaries together. So we're going to have 1 over 2 ux, and we have minus 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 v of y plus I x, and then this thing, so v of x plus u of y, that's a double integral dx dy, and then that thing is 1 over 2 omega divergence of this expression. So let's write u minus v plus I times the divergence of v of x comma u of y dx dy. Yeah? Like this, yeah? And then we apply the divergence theorem. So we have 1 over 2, and then integral like this, and then this will be u minus v dot product tau, where tau is going to be the outward pointing unit normal to our boundary like this, okay? So, and this is around this thing. Around the boundary, of course. So I'm going to write just ds to indicate integrating around the boundary in the standard way we've talked about, just a one-dimensional line integral. Actually, previously I wrote dh1, so let's be consistent. Let's be consistent. Like this, and then 1 over 2, damn it. And then like this, v u dot tau dh1, like this. Okay, so this is just applying the divergence theorem, yeah? All right, so what is this thing? This is 1 over 2, integral like this, and this is u times tau 1 minus v times tau 2, like this, dh1 of s plus I over 2, integral bound of this, so we have v tau 1 plus u tau 2, h1 of s. And now we want to flip this around and then consider the dot product of the tangent going anticlockwise, right? So if we have tau, which is tau 1, tau 2, right? Then flipping it anticlockwise, so that it points along the tangent like this, so it's the same as I times tau, then actually I don't want to write that because I'm thinking about this still as real, so like I'm going to write it like this, then tau like this is minus tau 1, tau 2, yeah? So if we do that, then we're looking more like we're doing these standard contour integral. So then let's write that. So that's 1 over 2. Missing the boundary. Boundary of omega. So that's the same as v comma u dot product minus tau 2, tau 1, dh1 of s plus I over 2, like this, and I'm flipping this around, so this would be like minus u v dot minus tau 2, tau 1, dh1 of s. Yeah, so if we do this, then we can get this, and this gives us this. So these are the same expressions. Yeah? Cool. So why are we doing this? So let's put it in the form of let's pull out this. Let's pull out this minus I over 2. So if we do that, then divide through by minus I over 2. So then we have minus I over 2. Omega like this. Then all this stuff becomes minus, so we're going to have u minus v dot product minus tau 2, tau 1. And then if we pull out minus I over 2 from this, we can write 1 as minus I times I, right? So then we'll just have plus I of v u dot minus tau 2, tau 1, yeah? dh1 of s. Now, if we do the following, let's multiply u plus iv. So we should have tau 2 plus I times tau 1, because this is this anti-clockwise guy here. So let's multiply this thing out. We have u times, or minus u times tau 2, this times this, and we're going to have minus v times tau 1. That is the real, and the imaginary we have, let's put this u times tau 1, this one times this one, and then minus v times tau 2. Is that what we got? So let's check this. Yeah, that's right, good. And then u times tau 1, and then, yeah, okay, so this is exactly what we want, yeah? So let's put this little calculation in the box over here. That means that this thing, running out of space, is minus I over 2, and I keep forgetting to put the boundary signs like this, and the boundary signs like this, integral around the boundary. And then now we're just going to write this in this form, right? So it's u plus iv complex multiplied by minus tau 2 plus I times tau 1, like this, ds. Yeah? Cool. But if we take the parameterization z prime that goes anti-clockwise around this thing, yeah, then this is exactly the same as, so let me write this over here. So z of 0 to a around the boundary of omega, then z prime of t will be minus tau 2 at the point z of t plus I times tau 1 at z of t. Yeah? Cool. And so then this thing will indeed exactly give us the integral now in the complex sense of the function f dz. Yeah? And that's our identity like this. Yeah? So this is a complex notation way of writing down essentially the divergence theorem, but it's going to be very useful for us. All right, everybody with me? Everybody happy? All right, cool. We're going to apply this to the following function. So take phi belonging to w1 to omega. Let's assume it is continuous, because I think this is more specifically where they took something to be continuous, and then pick some z belonging to omega. Omega's open, it has a nice boundary, so omega boundary is nice. And then we're going to apply this to the function, apply previous formula to the function tau goes to phi of tau over tau minus z. Okay. What do we know? We know that if we take the double integral of omega and we take the partial with respect to tau, so it's a function of tau now, so tau bar of this thing, phi of tau over tau minus z, like this. And I'm going to write d tau, because I'm integrating with respect to tau. Then this thing is minus I over 2, the integral around the boundary of omega of phi of tau minus z d tau. That's applying the previous formula, right? And this thing, so we're taking the derivative with respect to z bar, so we would apply the product rule, but we're applying it to something where the derivative of this guy is going to be 0 when we differentiate with respect to tau, right? So if we take any, so take any holomorphic function f, then df by dz bar is going to be just 0, because df by dz bar is just going to reduce down to the Cauchy-Riemann equations, which this thing satisfies, right? So when we do this, we apply the product rule. We will take the derivative with respect to tau bar on this thing, and then on this 1 over tau minus z. But on this 1 over tau minus z, it'll actually vanish everywhere. Yeah? Except at z itself, where we have a singularity, but that's only at one point, and we integrate respect to the weak measure. So this thing, I claim, is just the same as doing d phi by d tau bar, extracting out the conformal derivative, and then integrating this tau minus z d tau. Okay, this is what I claim. Yeah, and then we're going to look at this guy. So we're going to actually choose omega to exclude a small ball of radius epsilon around z, like this. Like this. This is going to be the boundary of omega, take away a small ball of radius epsilon. Around z, like this. Okay, and we're going to have to think a little bit about this, because this is potentially omega, right? This is the small ball around z itself. We're doing the anti-clockwise orientation, right? But when we do the anti-clockwise orientation around this inner part, we end up going clockwise, because the anti-clockwise orientation is what happens when we take the outward pointing unit normal and then turn it anti-clockwise by 90 degrees. Right? When we take the outward pointing unit normal here and we turn it clockwise by, anti-clockwise 90 degrees, then we end up pointing clockwise. So then this thing is actually going clockwise around this inner thing like this. Like this. Yeah? So then, what happens? Then we can break this thing down into its two parts of the boundary. So we have this minus I over 2, and then the boundary of omega, this is the standard thing, phi of tau over tau minus c d tau. But now, oops, this is a minus sign. But now we're going to have the integral around the boundary of the circle, but going round clockwise, which is going to put another minus there. So I claim this is now plus the integral of the boundary of epsilon z tau, oops, tau over tau minus c d tau. Is everybody happy with why we get a plus here instead of a minus? Yeah? Thumbs up if you're happy, thumbs down if you're not. Okay, cool. So if we look at this term a little bit more carefully, this is stuff that we can understand just from the methods of complex analysis. So look at this. If we do integral around boundary of all the kind of tools we did in complex analysis. So if we do this, we're going to take our parameterization. Standard parameterization of this thing will be z of t is bad choice. Let's call it zeta of t is equal to z plus epsilon e to the it, like this. So then this will be the integral from 0 to 2 pi of phi of z plus epsilon e to the it. And then when we subtract this, we have epsilon e to the it like this, and we take the derivative, we are going to have epsilon times I e to the it dt. Yeah, and then we'll have this cancellation of this and this, and then what happens? Well, as we get closer and closer to, as epsilon gets closer and closer to 0, since this thing is continuous, this guy here tends closer and closer just to the value of f at z0. Yeah. So if we put limit signs inside this, so limit as epsilon tends to 0 equals limit as epsilon tends to 0, it's just going to be 2 pi I times phi of z, like this. Yeah? Cool. So when we put that into that expression, then we'll have that So we're going to take the limit of this thing as epsilon goes down to 0. So limit as epsilon goes down to 0 of omega take p epsilon of z of this thing, phi by d tau prime of tau over tau minus z d tau. Okay. Then this thing, well, this thing will just be the same as, well, okay, no, okay. So this thing will be the principal, the principal value of this singular integral. So, all right, let's just keep it this way, and then I'll talk about it in a second. So we have this thing is equal to this guy, so minus I over 2 integral like this, tau over tau minus z d tau. And then this guy, which we've worked out, is just 2 pi I times this. So we're now going to have this is just minus pi times this expression. Oops, minus pi times the value of the function, phi of z. So then we can clean that up. We can put that guy on the other side and this thing on that side, and we're going to have that phi of z is equal to minus I over 2 pi, this thing, d tau, right? And then minus this thing, and it's divided by pi. So 1 over pi, then this thing. And, forgot the limit signs. Limit as epsilon tends to 0 of 1 over pi, like this. And then phi by d tau, like this, tau over tau minus z, and d tau. Okay. And then what we're looking at is a generalization of Cauchy's integral formula. So if we had a holomorphic function, then there would be no d phi by d tau, d phi by d tau bar. There will be no anti-conformal part. So this entire thing would just vanish, right? And then this thing, this is the same as this, right? As this. Yeah. So excluding that part, we're looking at exactly Cauchy integral formula. Yeah. So this is generalized Cauchy integral formula. So see you on Friday. Have a good day.